Hello, today we're going to do flowcharts and binary calculations. So before we look at flowcharts, we're going to look at the symbols and what they mean so we know how to use them when we're making our flowcharts. So first of all, we have determinators, which basically just define the start and the end of the algorithm. So just look like that. It's pretty messy, but you get the gist. So that goes at the start, goes at the start, and goes at the end of the algorithm. So these are very essential, and you actually get marks for having these in every single flowchart you'll get marks for these. So even if you don't know what to do for the flowchart, it's always good to just put these. Now the second one is the process symbol. It is for an action that needs to be carried out, like a calculation or variable declaration, basically. So it's a pretty simple one, it's just a rectangle. Now, the third one we have here is the data symbol. It's used anytime you just need to take an input or an output or output a value. So whether you want user input or you're trying to print something out, that's when you would use it. Now, the fourth one here, we have this diamond shape, and it is for selection. It basically, it denotes a decision to be made. So basically, it will ask a question. If the answer is yes, it will take a particular action, and if the answer is no, then it will do another action. So basically, this is the same logic that is used in if and else statements. So it can be used for that, and it can also be used for loops to continuously loop the program. Now here we have obviously something essential, which is the arrow, which just shows the logical flow of the program. So you always need these to connect your shapes. So if you just have like your shape, it's not very good, but yeah, if you have your shape, you always need the arrows connecting. The arrows must be touching the shape. And lastly, we have the subroutine shape. Now, basically, if you haven't learned what a subroutine is, it's just a higher level of decomposition where it's basically an algorithm inside of an algorithm. If you haven't learned it yet, though, don't worry about it. Okay, now we're gonna look at a flowchart. So here we have the start terminator. Tick. We have the arrow, and then here we have a user input. So as you can see, they use a parallelogram, which is the input-output shape, and it says height equals user input. So this is the same as saying, height equals int, and then print out whatever, please enter your height. So this will take the height as an input and store it as a variable. Now same for width, it uses the input output, and here we see the process rectangle. So it says that area is equal to the height times the width, which creates a new variable area, which is equal to obviously the height times the width. And then finally, it will output the area, and then for the user, and then obviously you must have the end block. So here, this is an example of a pretty simple flowchart. A little bit more complicated flowchart. So we have the start, and then it sets count equal to 1. Now here we have our decision block. There was a 1 in the last one. So here it says, asks a question, is count less than 11? So if that's true, it's going to basically kind of start a loop almost. So it will output the count, which will be 1, this statement. So it will just output 1, and then it would do the process count equals count plus 1. So it would increase count by 1, so it would be equal to 2 now. And then it goes back to here, and then goes back into the decision. Is count less than 12? Well, count, we know, is equal to 2, so it's less than 11, so it's true again. And it's just going to output the count, which is going to output 2, and it's going to increase it by 1. And then it's just going to keep doing this and keep doing this and keep doing this until count is equal to 11. And when count is equal to 11 and this decision is made, is count less than 11, that is false. because count is equal to 11, so it's not less than 11. So then at that point, basically this loop will stop and the program will end. It will go here and it will go to the end terminator. So now we're gonna do some binary calculations. We're gonna start off with a simple binary calculation. We're gonna be converting denary into binary, and then after that we'll convert binary into denary. So to start off, we're going to be converting denary number 45 into binary. So what I like to do first is write out all the columns. It will usually be 8 bits that you're working with, and then it's pretty simple. All you have to do is check if the number, well, we're going to start from left to right, and we're going to check if the number fits into 45. So we'll start, does 128 fit into 45? No, it doesn't. Does 64 fit into 45? No, it doesn't. Does 32 fit into 45? It does. So we'll put a 1 there, and that means that we'll have a remainder of 23 left, because 45 minus 32 is, sorry, not 23, is 13 left. So now we check, does 16 fit into 13? It does not. Does 8 fit into 13? It does. So now we are left with 5, because 13 minus 8 is 5. So now we're going to check, does 4 fit into 5? It does. Does 2 fit into 1? It does not. Does 1 fit into 1? Yes. Done. That is the denary number 45 converted into binary. Okay, so now we're just going to be doing the opposite. We're going to be converting a binary number into denary. So first we draw the columns, and then we will write out the binary number. So like that. Right, so now that we have written out the binary number, we'll just add up each number that has a 1 in front of it. So it's going to be 128 plus 16 plus 4 plus 2. Now you have to do this in your head. So it's 16 plus 4 is 20, plus 2 is 22, 128 plus 22 equals 150. And that is how you convert from binary to denary. Okay, now we're going to be doing signed and unsigned integers. So basically an unsigned integer is basically the same as what we were doing before. It's just each number represents a specific integer and everything's the same. But for signed integers, this is how we represent positive and negative numbers. Well, it's one way we represent positive and negative numbers with binary. So with signed integers, basically the most significant bit, which you might see sometimes as the MSB, well, which is basically the bit for this to the left, is basically taken up, and if the most significant integer bit is a 0, that means the number is going to be a positive number. However, if the number is 1, that means it's going to be a negative number. So basically the downside of this is that even though we have an 8-bit number, we can't represent as high as a number as if it was unsigned, because this basically has no value. It's just a 1 to show if it's negative, or 0 to show it's positive. So basically we can only represent up to 127 and minus 127 with signed integers, unlike you can do up to 255. You can do 255 for unsigned. So yeah, basically let's give it a try. So let's say we want to convert, let's say minus 17. We want to show minus 17 as a binary number. So first of all, we'd have to put a 1 in the MSB, the most significant bit position, and then this minus. Basically the rest is just the same. So does 17 fit into 64? Nope. Does 32? Nope. Does 16? Yes. Does 8? No. Does 4? No. Does 2? No. Does 1? Yes. And then basically this shows the number 17, and then this most significant bit shows that it is a negative number. So now we're going to look at another way to represent positive and negative um, binary numbers in binary, which is 2's complement. Now, one way in which this is similar to signed integers is that you put a 1 at the start to represent a negative and a 0 at the start to represent a positive. Now, the difference is when you put a 1 at the start, instead of just representing plus or minus, this now represents a minus 128. And basically every number you add on, so let's say you go 0 0 0 0 1 1, this number would be minus 130 minus 125. Now this is because every number you add on afterwards is basically subtracting from 128, making it bigger. So this would be minus 2 minus 1, which is minus 125. So with and obviously the zeros, just nothing happens with those. Now here we can see on the top that with 2's complement you can represent minus 128 to 127. That is the range of numbers. Now that we understand what 2's complement is, though, we can complete this question. So there is a way, a simpler way to convert denary numbers into binary into 2's complement than what I just showed. So first of all, you write out the denary number. So basically we would just write out it's minus 72, but we would just write it out as if it's 72 for now. So as a binary number, 72 would be dot 0, so 0 1 0 0 0, and now we have represented the binary denary number 72 in binary. So now what we have to do is we flip all of the bits. So now we're just gonna make a new line, flip all of the bits. So 128, 0 becomes 1, 1 becomes 0, 0 becomes 1, 0 becomes 1, 1 becomes 0, 0 becomes 1, 1, and then 1. And here, this is not the final step. Once we have flipped it, there's one final step, and that is to add 1 onto this number we have. So let's add 1. So 1 plus 1 is 0, 1. 1 plus 1 is 0, 1. 1 plus 1 is 0, 1. 1 plus 0 is just 1. And then 1, 0, 1. And the rest is the same. So basically what we've done here is we've just added 1 to this number. And this will now represent minus 72 as a binary number. Thank you for watching, and don't forget to subscribe to the YouTube channel. GCSE help.